A special type of function exists called the modulus function, and that's what we're going to look at in this video here. Now this function is essentially looking at only positive solutions of some function of y. The way to think about it is this. The modulus function, which we also call the absolute value of x, now we've heard that phrase before, absolute value, and it's being denoted by this, so y equals this sort of function poo. So a special kind of function exists called the modulus function, and that's what we're going to talk about in this video here. It's a function that has a special format and only looks at getting positive solutions out for every value associated with the function put in. Now we also call the modulus function the absolute value of x. So what this means is we are only taking the positive answers that we get. Now this is denoted by this functional format here. What we call this is y equals the magnitude of x, i.e. the size of it. What this means is the magnitude of x gives me a solution of x when x is greater than or equal to 0, or a solution of negative x when x is less than 0. So what that means is, let's say I had a value of -1, the value I would want for my final solution is -1, which would be 1. Easy way to think about this is essentially it's whatever value x is, but ignore negative signs that are associated with it. So only wants positive answers out. Now a function like this, a function in this form, has several key properties, each of which we need to make sure we remember in order to be able to work effectively with it in future endeavours that we're going to look at. First property is that the magnitude of x can be represented by the square root of x squared. So if we take any value of x and we square it, what that instantly does is actually gets rid of the negative part associated with the function. If we then take the square root of it and only look at the positive value, that's what we get. If we then take two values, x plus y, and take the magnitude, i.e. look at the size of that, what we know is that that's going to be less than or equal to the magnitude of x plus the magnitude of y. So let's say for this example here, I give you x is -1 and y is equal to 2. If I do the magnitude of -1 plus 2, well that's going to be is -1 plus 2, which is equal to 1, so it's the magnitude of 1, which is 1. If I look at it the other side, and I do magnitude of -1 plus the magnitude of 2, well the magnitude of -1 is 1, plus the magnitude of 2, which is 2, so that's going to be equal to 3. So what that means is that this form here, x plus y, the magnitude of it, is less than the magnitude of x plus magnitude of y. So this property here holds. The third property I can then associate with a magnitude function is this here, that if I take x times y, calculating the magnitude of it, that's the equivalent of doing magnitude of x times the magnitude of y. So let's stick with x being -1, y equal to 2. If I do x times y, so let's do x times y, I do -1 times 2, so I get -2. If I then take the magnitude of that, I get a solution of 2. If I take the magnitude of x times the magnitude of y, I do the magnitude of -1 times the magnitude of 2, I then end up with 1 times 2, which is equal to 2. So I get the same answer out if I were to do that. So this property here holds for those values and holds for all the values of x and y. What I can then say from a fourth property is if the magnitude of x is less than or equal to a, what that would mean is that the values for x would lie somewhere between -a and a. So the value I originally put into the modulus function would lie between there. So for example, let's imagine the magnitude of x that I've got here is less than or equal to 1. What that would then mean is that for x, the original value I put into the function, I could choose any value between 1 and -1, and this would hold, so my solution is correct. Fifth property states that if magnitude of x is bigger than or equal to a, what that means then is -a is bigger than or equal to x, or x is bigger than or equal to a. So for example, let's imagine, we'll stick again with that same value, that my magnitude of x is bigger than or equal to 1. So if the magnitude of x is bigger than or equal to 1, that means either x is bigger than or equal to 1 itself, or -1 is bigger than or equal to x, i.e. any number between -1 and -infinity would give me the same solution. So there are 5 key properties of modulus functions that we have to work with, we have to remember, and we have to be able to denote. And this all comes in handy as well when we're looking at graphs of modulus functions. So if I look at sketching any modulus function, the essential way that I have to remember it is if I take any f of x, so let's take this as an example, any negative sections of the curve get reflected in the x-axis and get drawn above it. So if I was to take this function as an example here, notice I've got a curve that goes below the x-axis, back up, then below again, then back up. If I were to plot the magnitude of that function, it would come down to the point where it was going to cross the x-axis here, but then at that point, instead of continuing down, this section gets reflected back up over the x-axis. I then do that up to this point here, where I would have cut the x-axis again, and I follow the same functional form that I would there. And then at this point, when it goes back below the x-axis in the original, I just reflect it back up over the x-axis here, to the point where it would intersect the x-axis for the final time, and then just continue off as I would. So essentially, it's just mirroring every single negative section back up and over the x-axis. So I'll show you a couple of examples of what I mean with that. Let's imagine I'm going to sketch the curve of y equals f of x, and then y equals the magnitude of f of x, and I'm going to tell you that f of x is equal to 3x minus 1. So that's quite nice. It's a nice straight line function. When we're looking at straight lines, remember if we think back to Nat 5 and higher, what we do is we look for an x-axis intercept and a y-axis intercept. So from a y-axis intercept, x is equal to 0. That means it's going to cut down here at -1. And from my x-axis intercept along here, 3x minus 1 is 0. So I know that x is going to equal a third. So I know it's going to be a straight line that cuts through those 2 points there and heads off to infinity. So that there is my y equals f of x. Now, for doing the modulus of f of x, we have to remember that basic rule that we said there. Anything below the x-axis gets reflected back up. So if I look at this section here, nothing's going to change. I'm still going to get where it would have intersected at a third, and it's still going to continue off and be positive. However, below a thirds, what happens is it goes down into the negative. To plot the magnitude of f of x, I just reflect all of that up, and it would then head off in the same direction there. Now this point of intersection here also gets reflected up. So it originally was -1. When I take the magnitude of it, it goes up to 1. So the function looks something along those lines. If you're ever asked to sketch something like this, these key points of interest, so my y and my x-axis intercepts, have to be shown in the new graph. So they have to be shown as, this is where it's moved to, I understand what I'm doing. Same for more complex functions as well. So let's imagine that f of x is equal to sine x between 0 and 360 degrees, and I want to do the same thing. Plot y equals f of x and y equals magnitude of f of x. Well, the graph of sine x is one that you should know by now. We've covered it many, many times from S1 all the way up to S5. It's a curve, looks something like that, and you should know the key points on the curve. So you should know the highest point is 1, the lowest point going along there is -1, and you should know where all of the key points occur. So this one here occurs at 90 degrees. Now, when we are working with advanced higher, we tend to stick to radians. If I was to put 90 degrees here, I'd be fine, but you could also call it pi over 2. This point here would be 180 degrees, or pi, if we were working in radians. Here, it would be 270 degrees for the minimum, or 3 pi over 2. And then this final point here occurs at 360 degrees, or 2 pi. Again, I've gone from 0 to 360 here for the graph, just for ease of drawing it the now. You would be asked probably to work with radians at any point in what we're doing. We then want to figure out what the magnitude of f of x is. How would that look? Well, the initial part of the graph is going to stay the same. Remember, we want everything to be positive and above the x-axis. So this little section here from 0 to 180, 0 to pi, stays the exact same. None of the points of interest change. So I've still got 180 where it would intersect. I've still got my 90 degrees, my pi over 2 there, and my highest point is still at 1. What now happens is this entire section here is reflected up above the x-axis. So what now happens is instead of going down, this section here goes up as well. But all these key points have to be maintained and shown how have they transformed in the new graph. Well, this lowest occurs at 270, so my new high point of interest there still occurs at 270 degrees, and it still hit the x-axis again at 360, so it's still going to hit the x-axis again there at 360 degrees. Now my lowest point was at -1. Again, when I flip it up and it becomes positive, the height doesn't change, so I can extend that and mark it on there. So in this case, that's why it was the magnitude of f of x. Sketching the modulus function is actually quite straightforward. We just have to remember those key rules and those key points. Flip it above the x-axis. If it goes below, make sure that you understand that, and make sure that you understand how to calculate the modulus of a value. Essentially, get rid of any negatives that are there and just look at the size of the number that's associated with it. These are key things you have to be able to work with at advanced higher, and key things that you need to remember. So make sure you go away, you work at these, you look at it, and you understand all the parts to do with this.